Thank you very much for the opportunity to speak, despite the controversial title. So I should start from a disclaimer that I will not present any new results. All this is just interpretation. So what I want to do is to just draw some attention to the ideas which has been going on in the black hole physics regarding the complexity and how they are related to all these modern developments of cryptocurrencies, how complexity works there. And obviously, I will not assume that people in this audience know much about cryptocurrencies or blockchain. So I will explain everything. So at least if you did not know about that, I hope after my presentation you will understand how things work. Yeah, but one thing I will not do is that I will not give you any investment advice.
Alexey, did you do sort of like the assay for gravity research or something?
Yeah, yeah.
Oh, cool. Okay. Yeah.
So let me just in one slide briefly review what's going on with the black holes. So there is this celebrated Einstein-Rosen bridge solution when I have two universes connected with a bridge. So at the, let's see, very good. So at the entrance to this bridge, there are two black holes, and inside we have a growing interior. And the volume of this interior grows with time. It can become as big as e to the s naught, where s naught is the Bekenstein-Hawking entropy. And then the question is, what is the counterpart of this quantity, say, in a DSCFT? The difficulty is that all usual thermodynamic quantities are extensive. They are proportional to the number of degrees of freedom, whereas this guy can be exponentially big. And it prompted Susskind and friends to propose that volume should be dual to computational complexity. So in the quantum world, what they proposed is that roughly this volume should be something like this. So we start from some simple initial state, with time evolve it, and then we look how difficult it is to prepare this state. Difficult in the sense that I have a dictionary of elementary gates, and then V should be proportional to the number of gates required to prepare this state. And it's not difficult to show using simple combinatorics that this complexity can be indeed as big as e to the number of qubits. So now this is one logical step I want to make further. So colloquially, when we go outside black hole horizon, we switch space and time. For example, in higher dimensions, we will have to switch volume and time, but in, say, in 1 + 1, it's exactly that. We switch the length to time. And so more generally, without any black hole interior, we can speculate that complexity is equal to time in some sense. And I wish I had more physical example to illustrate this correspondence, but what I would like to explain is that this slogan, complexity is equal to time, is the foundation of modern blockchain protocols and cryptocurrencies.
Can you go in the previous slide, can you explain again this idea of this? So what is this? So you start from some fraction. Yeah, this picture.
Yeah, I start from some simple state. So the question is, what is the computational complexity and how big it can be? So the idea is that I start from some simple initial state, and then I time evolve it. Or I can consider some other state in my Hilbert space. And then I have a limit. So in general, if I'm allowed to do any unitary operations, then obviously I can just do this transformation between the two states in one step. I just apply unitary. But the idea is that we are limited, say, by locality. So we only want to apply two gates. And so I have some universal, meaning that I can obtain every state this way, but limited dictionary of gates. And then it turns out that this this complexity of state preparation can be actually exponentially big. So this is some quantity which does not necessarily extensive in the number of degrees of freedom, but can be exponentially big.
So it's exponential in the number of gates or in the number of
in the number of zeros and number of qubits. So it's roughly the number of qubits, very roughly is the Bekenstein-Hawking entropy. It's the number of few degrees of freedom.
And each time you have this is a unitary, local unitary operation that you do between two qubits?
For example, yeah. I think one of the challenges, in this picture is to say what exactly, this complexity is. I think quantum information people had lots of complaints because there are at least 10 different ways how to define complexity, whether it's local gates or strictly local or maybe too local. So I'm allowed to make operations with 2 qubits at a time, but they might be separated. Or maybe I'm also allowed to include some ancilla qubits. So there are like a zoo of definitions, and this is more like a broad picture. But it has been checked in some sense. There are some consequences of this correspondence that there are some effects. There are some limited number of phenomena we know about this state preparation complexity. And all these phenomena can be reproduced using the semi-classical gravity. Yeah, if you have more questions about this, I can point the precise literature where it has been done.
Yeah, what I would say, just in addition, right, is that now even using non-perturbative gravity, you can start testing, if like the length saturates.
Yes, that's right. Yeah.
So there's even some more hints that this is something that is capturing complexity.
Yeah. So as a bonus point, we will see that blockchains have natural error correction. So let me also, before I jump into a blockchain, let me make a vague comment about AR equal EPR. So there is the famous proposal by Milekhin and Susskind that in certain cases, large quantum entanglement leads to a connected semi-classical space. But the quantum entanglement is a property of a given state, of a Cauchy slice. But really, gravity is not about just Cauchy slices, but it's about space-time. And ideally, I would like to argue that complexity is responsible to actually generating time evolution. So in this nice dictionary between quantum mechanics and gravity, we can treat entanglement as spatial connectivity, and time dynamics is dual to complexity. But this is, again, just some words. Let me now jump into blockchain. So from now on, I assume that everything is classical. So this is one thing I'm still trying to understand, what would be the quantum picture. And there are some proposals in the literature how to make quantum blockchain, but in this talk I will not mention this at all. So for me, classical complexity is not the complexity of time evolution, but more like just how much time it takes, how much computational resources it takes to multiply matrices, just complexity of doing arithmetical operations. So we have n independent observers, and they all have some computational power, and they produce classical messages. And they exchange them independently, meaning that there is no central authority they report to. Each observer produces some new message and share this message with its peers. And then we ask, how can they still arrange these messages in some fixed order? So for me, time would be nothing more just the ability to arrange the messages in some fixed and ambiguous order, which is the same for all observers. And one way to do this is to synchronize clocks, for example, but then clock synchronization might not always be possible, and it's also subject to errors or attacks. So clocks can easily desynchronize, and then we wouldn't be able to actually, observers will not be actually decide between themselves whose clock is wrong. Because if it is just me and Hugo, and our clocks are different, we cannot say which clock is right, because there is no, if we assume that there is no central time, we can compare our clocks to, there is some paradox we cannot resolve.
So what do you mean oral events?
Sorry, say it again?
Time before oral events?
Yeah, this is what I meant, that for me, time is not some, complicated metaphysical thing. For me, time is just how these messages are arranged. So how each observer arrange the messages.
Literally just order.
Yeah, literally just order.
So in a sense, you don't know which time you're at, because you know just the local information, but is that sort of like a global event?
Yeah. So the thing is, you only collect information locally, but this arrangement of events, if it is the same for all observers, which I want, it will be like a global thing.
Okay.
So is it a dynamical system, or?
Yeah, it's a dynamical system, yeah.
And what do they send each other?
Just classical bits.
And the bits, okay. I'm just don't understand what these two orders mean.
For example, okay, let me give you some example, like just in a bit into slides. What can be?
Sorry, are you allowing for relativistic exchanges?
Okay, good question. Well, all this has to be seen as living sort of in one space point. So I will not. I will assume that there is some fixed bound on the message time delivery. So I will only assume that if I send message from here to there, it will take some no more than delta of time units to actually get this message across. So, but I think short answer to your question is no. It's like purely classical thing with no relativistic effects. Although some relativistic effect in the sense that this time, which takes to message to go between two observers, it does not have to be fixed. In some sense, we have a fluctuating geometry there.
I mean, I was just referring to the fact that you know which event came first.
Yeah, good. So this you don't know and have to arrange for. So this would be the problem we're solving. That, for example, there's Alice and Bob, and Alice sends something to Bob, and then sends something to Carol, and then Carol gets it right away, and Alice event, is the next one in the Carol's queue. But for Bob, it might not be the case. Maybe Bob received something from Davis in the meantime, and so there will be a different order of events recorded by Carol and Bob. But I will explain this in a few slides. So two natural requirements for time is all observers record the same history. In other words, they have a consensus among themselves what was the order of events in the world history. And we also should prohibit time travel. And blockchain is capable of doing both. So let me now explain what might go wrong. So suppose Carol wants to divide the inheritance between Alice and Bob, and then there could be a problem. So not related to order of events, but also what actually information sent. This is the error correction I promised you. So Carol can send Alice message that Bob gets everything, and but to Bob she sends that Alice gets everything. And now there is no consensus among Alice and Bob, because up until this point, up until this confusing message, they were on the same page. They all arranged the events in the proper order. But after this message, their history is different. So in Alice's timeline, Bob gets everything, and in Bob's timeline, Alice gets everything. And this is not consistent. We cannot say that, okay, there is a globally defined state of things right now at this stage, because not all observers agree on what is going on. And we should be able to fix it somehow. Another problem is time travel. So suppose initially Carol says that, okay, Alice gets everything, and this is consistent, and everything is fine. And based on that, Alice buys a house. Yeah, sorry for making this too anthropomorphic, but I hope it helps understanding. But then, okay, Alice buys a house, but then Carol suddenly changes her mind and says, okay, Bob gets everything. And then it's very confusing because Alice bought a house conditioned on getting the inheritance. And now it's not just the problem of Alice, it's also the problem of the real estate company she bought the house from. So it's like errors will propagate and so on. We want to prohibit this from happening. So somehow, despite the fact that Carol distributes the inheritance, Carol should not be able to change her mind and go back. So how does blockchain solve this? So first of all, it enforces a 1D structure on the on how events are recorded. So as follows from the name, blockchain is a chain of blocks. So each block contains useful information, who gets the inheritance, and some extra data. And this extra data are used to so that we can create these two functions, create and verify. So what is important that when I create the next block, when I create the next block, all the information stored in the block, both useful one and the technical one, it depends on the previous block. So this function create takes block n-1 and useful data and arranges into the next block. And this is supposed to be a computationally complex function. And we need another function, which is verification, which verifies block n given the previous one. So take away from this is 3 steps, is that blocks are linked. So it's for to talk about a given block, we should also know what was the previous one. And then it's difficult to create block, but very easy to verify if this block is valid or not.
But how does that help creating this global time?
So it was just the first step, sort of like a local structure how we arrange the data. The next step is to enforce the global structure. So if I go back to this example with the inheritance, so I have some well-defined, consecutive history of events, but then Carol, either on purpose or as a mistake, creates 2 blocks. So 2 events where Alice gets all inheritance or Bob gets all inheritance. And now we have a fork in our time history, so it can go either like this or like that. So we need somehow to distinguish these two. And this is in fact the central point of Satoshi Nakamoto paper on Bitcoin, is that they proposed that the longest valid chain is the correct one. And this is really the central point of all this blockchain business. So longest can be substituted by the words most complex, because classically we can assume that creating each block has approximately the same complexity. And well, in some sense, this is similar to maximizing a time like geodesic. So if I have just one spatial point, and so all my history of events are located on this space point, but I want to distribute them somehow along the time like geodesic. So if I want to look at what is the current state of things, I should, extend the geodesic as maximally as possible. Well, this is maybe not the most clear analogy, but the global condition is the maximization of complexity, that really the history of events will be defined by finding the maximal complexity slice.
So can you give some notation for that?
Why what?
Why do you have to choose a maximally complex one?
I will demonstrate a few examples. Yeah, that it is this condition which allows us to resolve the disputes and prohibit time travel. So let me now revisit this case with the inheritance. So when Carol says that, okay, Alice gets everything and Bob gets everything, it's a tie essentially. We don't know which, what is the current state of the things. But this sort of fork, it will be spread around the system. So we need to, in fact, assume that we have many number of observers. And then each of them, this is in fact a part of the definition, that if there is a fork in the blockchain, observer who wants to add their information can pick up just a random branch. So this record will be spread around the system, and each observer will pick up a branch randomly and start adding their blocks. And soon after a few blocks are added, a tie will be broken, assuming that I have a large number of observers. In this case, the probability of remaining in the tie, it vanishes very quickly as the number of observers increase. So after a few blocks, the tie will be broken, and it will be like a system with positive feedback. So this is the longest chain. More people will have this copy, and they will keep choosing this branch to add new blocks. So this branch will proliferate, become longer and longer, and this one will be stuck. And so it is this event which will be recorded in the history.
Alexey, how do you guarantee that, like, these forks, for instance, in this example, doesn't happen sort of like uniformly distributed, and then
Yes,
you don't have
right.
a tendency to just go to one branch, sort of like equally distributed?
Yes, right. So in fact, the way it's done in Bitcoin is that, so roughly the idea is it takes a longer, well, you see I have a problem on my presentation, is that I on one hand want to define time, and so it means that I don't really want to refer to some other time. So, but the way it works in the real world is that it is so difficult to create a new block that time it takes to create a new block is much longer than the time it takes to actually distribute one. So what happens is that blocks occur very rarely, and this is why all participants have, in practice, all participants have the same have the same version of the blockchain. Because obviously, if this time is much shorter, there could be some local branches growing because the observers don't have enough time, to communicate between themselves. Yeah.
So it sounds like in this tie scenario, there's like the winner isn't really determined by veracity at all. It's just like whoever happens to come up with the valid block for one of the branches. So like,
Yeah.
like if somebody makes a fake block that's just not true, how does that get weeded out?
What do you mean fake block?
Like if somebody wants to add like a third option that is like,
You mean third option to here?
yeah, that's not true. Like I don't know, maybe like Carol burns her money or something. Like what stops that from being picked up as like in principle it's just like a random selection of which one gets the next block, right?
Yeah. So, okay, from the perspective of Carol, Carol can definitely do that.
Yeah.
So in practice, when we actually talk about money distribution and so on, in the real world, people also use public signatures to actually make sure that only Carol can say what to do with her money. But I don't think it has any physical counterpart, so I'm just suppressing this story. But in general, yeah, it's possible to add a new branch, yeah, and then it will be.
Can you also get rid of one of the branches?
Hmm?
Bob and Alice marry now. So.
You mean if they can merge?
Yeah.
No, this doesn't happen. Yeah, this. Sorry, it was very anthropomorphic, but instead of giving an example with inheritance, I can say, okay, I take this chalk and then I throw it up and put it down. So now some event happened, it's recorded in your memory, it's recorded in the memory of the universe. So now I cannot just go back and say, okay, no, this did not happen. So this did already happen. So I can claim whatever, but it happened. And the same with blockchain. Once there's something recorded there, that's it. But there is a little problem. Sorry. Why does it jump? Okay. So there is a problem because this consensus among the observers, what is the current state of things, it's probabilistic. Because suppose I add some new information, so I add a blue block, and then it seems that it's successfully added, it belongs to the longest branch. But then suppose I had for some reason, separated group of other observers who were working on a different branch on this one. And suppose, like as a pure fluctuation, there was a big delay in the communication, and so they in fact came up with an extended version of this branch, but this information did not become readily available. But when it does, it becomes apparent that now this is a dominating branch. And so all the information I added, it doesn't belong to history anymore. So it's a problem for freshly created blocks because there is a chance that, okay, maybe someone added something long to this block. And so my block also ended up in a dead end. So there are, in fact, the whole structure represents more like a tree rather than a chain because there are all these dead ends which don't have maximal complexity. But this probability of actually seeing an event belonging to the dominating slice and then the dominant switching to some other branch, this probability goes down if you go back in time, because for this newly created block, there is a good chance that maybe someone added something here, which I'm not aware about. But when it comes, for example, to this block, this is highly improbable because it means that someone has to actually add something here or here, and they have to add lots of blocks. And creating a new block, it's highly expensive. For example, in Bitcoin, it takes 10 minutes, to come up with a new block, which on the scale of modern computation, it's a huge time. And complexity is equal to time in the sense that the chronology of events is determined by finding the maximal complexity slice. So if you want to see what the history is, you find the maximal complexity slice, and this tells you what the unambiguous order of events which happened.
But that's all in hindsight, right? You have to wait.
Yeah. This is the problem. So this is one of the drawbacks. For example, in Bitcoin, it's customary to wait 3 or 4 blocks. So once you made some transaction, you should wait until 3 or 4 blocks more are added, and then it's like an industry standard to make sure that, okay, it's really there. And if you are a vendor, that you can now transfer your goods to the buyer, because you will be sure that, sure with high enough probability that you really earn this money now, that they are really transferred. But in general, it's a drawback, yeah. So 3-4 blocks, it takes like half an hour for a transaction, which is, in everyday life might be complicated. I mean, not very convenient. So now let me tell you why we cannot time travel. And this is related to the question why maximal complexity is, say, not minimal complexity. So suppose, okay, this I didn't put it here, but suppose on this branch, Carol transferred all the inheritance to Alice. So and here Alice bought a house on block N. So now at this stage, Carol's money doesn't belong to Carol anymore because somewhere, say, in block 2, she transferred all her money to Alice. So at this point, she will not be able to transfer the money to Bob because the money doesn't belong to her anymore. So what she needs to do is to create a new version of block 2 where money are transferred to Bob. This is like alternative history now. But the problem is that block 2 now contains like completely different bits. And so block 3 here, it will not be valid given the block 2 prime. So this is this function verify I talked about, that validity of a block depends on the previous one. And so Carol will have to concoct some full alternative history of events which happened after she transferred money to Bob. And so she will have to create block 3, a new one. But the problem is that if we assume that all observers have equal computational resources, it just will take her a while to do that. And in the meanwhile, all law-abiding observers will just extend this dominating branch. And it will extend much, much further. And Carol will not be able to catch up with them. So this is why you want to choose a maximal complexity and not minimal complexity.
So in principle, you could travel back in time if everybody decided that that's a good thing to do, right? Because then they stop extending that branch and just do another.
Yeah, right. This is my next comment. So in fact, so this a picture when you cannot change the past simply because future extends too fast, it's similar to the growth of the Einstein-Rosen bridge. So you can think about the fact that you cannot cross it because it grows with the speed of light. And so you can in principle cross it, but then you have to travel with the faster than the speed of light. But in principle, it's true. If Carol has more than 50% of the computational resources, she essentially, the master of the universe. She can arrange the history events as she pleases. So this is one important implicit assumption, that all observers have compatible computational resources. So what we saw so far is that time can be an emergent large chain probabilistic phenomena, meaning that I need many observers. And or even in this case, the current state of things is not defined with probability 1. There is a small chance that recent events might change. The question is, can we do better? For example, if we have small n of observers and we want to make sure at each time step what happened or what not happened. And in general, this problem is known as the problem of Byzantine generals. And the answer is, in fact, yes, you can do that, but with bigger restrictions. So first of all, in the previous slide, I mentioned that no one should control more than 50% of the computational resources. In the case of this Byzantine fault tolerance, it's no more than 1/3. And this is, in fact, a proven theorem. And another problem is that they're creating sort of a new history event. It becomes very complex. So in the blockchain, it was probabilistic, but what it took is to record a new event is just spread it around the system. So it was roughly the complexity of n if number of observers is n. So there are protocols who can do this non-probabilistically, For example, this practical BFT. But then complexity of adding a new block, it becomes quadratic. So in real life, if I have something like a distributed cache system, then it's not feasible if I have tens of thousands of people participating. But if I have a small number of elements, then it's doable. And in fact, I read that this sort of Byzantine fault tolerance is used in airplanes because you have many copies of the detectors and so on, and you don't want to rely on a central computer to decide, okay, if I have, say, 3 detectors and 2 of them give the same parameter, give the same reading, and the third one gives something different, I don't want to rely on a central computer to decide, okay, this one is a faulty one. I want to do this distributively. And so, in fact, this is how it's done in the airplanes with this practical BFT. If you have like a number, I don't know, 10 of elements, then it's this complexity of n squared is fine. So let me now maybe make some possible spiky example of what can be emergent time. But okay, I don't really elaborate this much, but this is just some random comment. So suppose I have k non-interacting SYK dots, then we know that in low energy limit I have the low energy dynamics is determined by reparameterization dynamics. But in fact, what happens if I even add a small interaction between SYKs, then classically it forces all the reparameterizations to be equal. So in fact, whatever the interaction you add, it will introduce a quadratic potential for reparameterization. So at low energies, they are forced to be equal. So this is in some sense even, and this happens even if you don't have a semi-classical dual. You can just imagine that you have 2 separate disks, and then you just add some hopping interaction between them. And even in this case, the time will synchronize in some sense. But I don't really know what to make out of this. Okay, let me now make, how much time do I have? Okay, perfect. So let me make some small comment just for completeness. So what I presented is formally called proof of work because it's very hard to add a new block. And it's its main drawback practically because it takes lots of electricity currently to mine all these bitcoins. So there are other approaches which are called proof of space or proof of stake, which allow participants to add a new block basically for free, but in exchange of some other resource. For example, dedicate some parts of their money as collateral in some sense, or dedicate some space on their hard drive. Yeah, but this, in this case, it's very easy to create a new block computationally, but it creates their own problem because if adding a new block is cheap, why not add many? And so I don't really know any good physical analogs of these other protocols because you need some extra ad hoc restrictions why each observer cannot just create many blocks on different branches and so on. Okay, let me summarize. So blockchain provides a model for an emergent decentralized time. It requires a large number of observers, and it's inherently probabilistic, but it has a natural bonus of having error correction. And it is emergent time in the sense that the chronology of events determined by finding maximum complexity slice. And this is similar to complexity equal to volume proposal for black hole interior. So let me now finish with the following thought. So it has been speculated that we live in a simulation. So let's hope that simulation is not someone mining cryptocurrency. Okay, this is all I have. Thank you.